Hello everyone, Science Spot is a podcast that shines a spotlight on the latest scientific technology from Japan. Your host is Ryan from SCIEN-TALK. Today's topic is solid cooling, and this is the final episode of the Refrigerator series. Solid cooling is a technology that uses a phenomenon where certain solid materials absorb or release heat when stimulated externally, for example, by pressure, stress, or an electric field. It's a bit like squeezing a wet sponge to release water and then letting go to let it absorb water again, but with heat. This absorption and release of heat is called the caloric effect. There are several types of caloric effect. For instance, the elastocaloric effect involves stretching and shrinking an elastic material like rubber. But the main focus today is on materials that use the barocaloric effect, which involves observing and releasing heat by applying and releasing pressure. The big advantage of these technologies is that they don't require refrigerant, making them much more environmentally friendly. Today, I'm shining a spotlight on a new material developed by a joint research team led by the Professor Shinichi Okoshi from University of Tokyo. This material holds the potential to spark a true cooling revolution. It's called rubidium cyan bridged manganese iron cobalt inorganic compound, or simply the Prussian blue. It's a long name, but simply put, it could become the heat and the heart of future refrigerators and air conditioners and a groundbreaking material from Japan. So what makes this material so incredible? It has achieved the world's highest adiabatic temperature change. Specifically, when subjected to pressure of 560 megapascals, its temperature dropped from 88 degrees Celsius to 3 degrees Celsius. That's an amazing 85 degrees decrease. This is the largest reversible adiabatic temperature change ever reported for solid refrigerant. It's like having a refreshing cold drink on a hot day and feeling your body cool down instantly. What's even more amazing is its durability. It was confirmed that the material maintained its performance even after repeating a 44 degrees temperature change and 440 megapascals of pressure over 100 times. This is a very important factor for practical applications. Furthermore, this material meets several essential criteria for practical implementation. For example, it shows an adiabatic temperature change of 21 Kelvin, even at a relatively low pressure of 90 megapascals. This allows for greater flexibility in system design and enables a wider range of applications. It also boasts high thermal conductivity, functions across a wide temperature range that includes room temperature, and is said to be cost-effective. It truly is a highly anticipated material for achieving the sustainable development goals and green transformation. And given its compact and environmentally friendly characteristics, this solid cooling technology is expected to have diverse applications. In electric vehicles, it could eliminate the need for cooling all solid-state batteries, contribute to increased capacity and extended cruising range, or even be used for motor thermal management. It's also expected to be a highly effective solution for CPU cooling in the smartphones and the computers you use every day, and even for cooling servers in data centers. As electric devices become more compact, heat generation issues are becoming increasingly serious. Of course, it's true that many of these solid cooling technologies are still in basic research phase. There are several challenges to commercialization. Materials fatigue and hysteresis during cooling cycles can reduce efficiency and shorten lifespan. Also, compared to traditional compressor-based system, initial costs can be higher and cooling capacity might be limited. And we'll need to demonstrate long-term reliability similar to the 10 plus year lifespan expected of household appliances. And however, to address these challenges, continuous technological innovation in material science are underway, such as the utilization of nanotechnology, the integration of hybrid solid cooling systems, and the development of miniaturization technologies for the microprocessors. The research results for this Prussian blue material represent an excellent example of how fundamental material science research can lead to innovative technologies directly addressing environmental problems. As a green transformation material, it is expected to make a significant contribution to future cooling technologies. So that's all today's Science Spot, and this is the end of the series of the refrigerators. What do you think about it? I'm expected to the future refrigeration. I was so excited to share the new technology and the history of registration. So I'd love for you to listen to the podcast and post your notes and the thoughts with the hashtag ScienceSpot, or I'd like to get your comments because I don't know how do you feel sequential episodes of this podcast. Thank you for listening and see you next time.